Today's topic is insertion loss. So it is defined as the reduction of signal power resulting from insertion of a device such as a filter, cable, or attenuator into a transmission line. So it is the ratio. It is defined as it is the ratio of power received before and after the insertion. So generally expressed in dB. Okay. So it is nothing but when in the transmission lines, if you insert a device like a filter, cable, attenuator, that will cause some loss. That loss is called insertion loss. So it is occurred due to the insertion of a small device. Okay. Generally, those devices also treated as two-port networks. So here the insertion loss is defined as the insertion loss in dB is given by 10 log base 10 incident power to the transmitted power. So this is nothing but this is the given power to the device. The transmitted power is the output power of that device. So whatever we have considered the filter or the cable or attenuator, attenuator. So due to the insertion of these devices, it will cause the insertion loss measured in dBs. So units are dB. Here the PI represents incident power. Incident power means the given power to the device, input power. Incident power. PAT represents transmitted power. Transmitted power. So it is nothing but incident power is the input power of that device. Transmitted power is the output power of that device. So this gives the insertion loss. Next, let us discuss about attenuators. Attenuator and pads. Attenuator and pads. So here, attenuator is nothing but it is the opposite to the amplifier. Generally, amplifier means it will increase the signal strength, where the attenuator reduces the signal strength. So quietly opposite to the amplifier. So coming to the definition of attenuator, an attenuator is a two-port resistive network. It is used to reduce the signal level when used between a generator and the load. So attenuators may be symmetrical or asymmetrical. So these are the two types of attenuators. They may provide fixed or variable attenuation. Generally, attenuator may provide the fixed attenuation or variable attenuation by adjusting some. Okay, so we can adjust so that it will change the attenuation. We can observe these attenuators in the function generators. So to reduce the signal strength in terms of volts to millivolts, we'll use that attenuator in dBs. So 10 dB, 20 dB are there in the fixed attenuators. We can observe in the function generator also. So a fixed attenuator is also called a pad. Here the pad means fixed attenuator. If it provides 10 dB, so always it will provide only 10 dB. Variable attenuator means at one instant it may provide 10 dB, at another instant it may provide 20 dB by changing the values. So here the attenuation is expressed in dB. Attenuation also measured in dB. So it is given by attenuation in dB. Attenuation dB, also given by 10 log base 10. It is the input power to output power. It's the ratio of input power to output power. So here P1 is input power to the attenuator. So P2 represents the output power of the attenuator. Already we have discussed attenuator is a device which is placed in between the input and the output, or generator and the load. So there are fixed and variable attenuators. Here fixed attenuator is called pad. So if you want to express not only in terms of powers, attenuation can also be measured in terms of voltage or currents. Sometimes we know only voltage, input voltage and output voltage. Sometimes we know only input current and output current. So we can express for a two-port network or for a device. So here P1 is expressed as I1 square into R naught, or V1 square by R naught. Here, why we are writing R naught? Is it the output resistance? No. Here R naught is the characteristic resistance. Characteristic resistance. Generally, we'll measure characteristic resistance when it is properly terminated or properly matched network. Characteristic resistance. It is not the output. Usually we'll give the suffix O for output. No. So properly terminated network. Here R naught is the characteristic resistance. For P2 also we'll write as I2 square R naught, or V2 square by R naught. So this is the expression for the powers, input and output powers. Then what will be the attenuation in dB? The attenuation in dB can also express in terms of voltage ratio or current ratio also. Attenuation in dB. So simply we will express the powers in terms of voltage or current ratio. So I1 square R naught by I2 square R naught. So if you take this ratio, we'll get, so whole square will get R naught and R naught gets cancelled. I1 by I2 whole square. If you keep this 2 outside, so this becomes 20 log I1 by I2. Or if you take the ratio of 10 log base 10. So V1 square by R naught divided by V2 square by R naught. R naught and R naught gets cancelled. Again, we'll get 22 outside. So 20 log of V1 by V2. So these are the expression for attenuation in dB. So there is another unit for expressing this attenuation, that is Napier's. So attenuation is also expressed in terms of Napier's. Napier's, N-E-P-E-R-S, Napier's. Attenuation is also expressed in Napier's as the natural logarithm, that is log base E. Natural logarithm of the voltage or current ratio. So attenuation can also express in another units at Napier's. Attenuation in Napier's. So attenuation in Napier's is given by natural logarithm. So this can be expressed as ln of V1 by V2 or ln of I1 by I2 or 1 by 2 ln of P1 by P2, P1 by P. So there is a relation between the Napiers and dB. Sometimes in the problem, they may give the values in Napiers, or usually we get the values input power or output power in terms of okay, generally power in watts, but they may give power in dBs also sometimes. So, or the attenuation in dBs. So this attenuation in dB can be converted into Napiers. So let us see the relation between decimal or dB, decibels and Napier. So we can easily relate, as we know the relation between logarithm, log base 10 and log base E. The same we'll use for getting the relation between decibels and Napiers. Decibels and Napiers. So let us see. So here attenuation in Napiers. Attenuation in Napiers is given by ln of V1 by V2, where attenuation in dB is 20 log base 10 V1 by V2. So this ratio is same. Voltage is measured in volts only. So V1 and V2 values are remain same. Now, if you want to relate these two, what we'll do is, let us take this 20 log base 10. So I will do this as 20. I will keep this unit as ln of V1 by V2 divided by ln of base 10. In logarithms, it is allowed that this, if you want to change the base, we'll do this one. ln of base E or log base E, V1 by V2, log base E 10. So this is same as log base 10, V1 by V2. Now, in this way, we can find the relation. So what this represents is, now for 20 into, so this is 20 divided by, this is 2.303 log 10 base E into ln of V1 by V2. Now we have changed the base to base E. So attenuation in dB is equal to 20 divided by 2.303. So if you measure that, we will get this as 8.686 ln of V1 by V2. So attenuation in dB and attenuation in Napier. So we can write this as 1 dB equal to 8.686 dB. Sorry, Napiers. 8.686 Napiers. One dB equal to 8.686 Napiers. Similarly, 1 Napier is 1 divided by 1 divided by 1 divided by 8.686 dB, that is equal to 0.015 or 115, sorry, 0.115 dB. 1 ampere equal to 0.115 dB or 1 dB equal to 8.686 ampere. This is the relation. So that's it for today. So in the next class, we will see types of attenuators. There are lattice attenuator, different types of attenuators we will see in the next class. Thank you.